table of contents include learning outcomes, introduction, the pi bonding taking place in the octahedral complexes according to the symmetry parameters, as well as the type of metal-ligand pi interactions possible. In this context, we will be discussing Pi acceptor ligands as well as pi donor ligands. We will compare both of them, that is pi donor ligands versus pi acceptor ligands. After learning this module, you should be able to know the difference between a pi donor and an acceptor type of a ligand. We will also learn the mode of bonding in various types of ligands. We will identify the symmetry parameters involved in the pi bonding. Also, we can analyze the modifications involved in the MO diagram with different types of ligands involved. First, the introduction. A more detailed description of bonding in the coordination compounds is provided by the ligand field theory as compared to the crystal field theory. For coordination complexes, ligands act as a Lewis base and donate a pair of electrons to the central metal atom, which act as a Lewis acid, and formation of a covalent bond takes place. This involves sigma bonding interactions, but the pi bonding interactions may also be considered as taking place. This involves the donation of the electrons from the ligand to the metal or donation of the electrons from the metal to the ligand. The later interaction is said to be a special name given as pi back bonding. We'll be discussing the pi bonding type of interactions in the octahedral complexes. First of all, considering the symmetry parameters. A pi bond has a nodal surface that consists of a bond axis with pi bonding orbitals having lobes of opposite sign on each side of this nodal surface. Considering a coordination octahedral complex, we can have a total of 12 such kind of bonds. This has been depicted in figure 1. But in the actual practice, such a number of bonds is never formed. If the ligand in the complex have orbitals with pi symmetry with respect to the metal ligand axis, they may give rise to a pi molecular orbitals on combining with the metal orbitals. This has again been depicted in figure 1. The ligand group orbitals that can form the pi bonds in the octahedral complex comes under the 4 type of symmetry categories, respectively, which are known as T2G, T2U, T1U and T1G. Table 1 is the character table, which is characters and irreducible components of the irreducible representation. In this context, the irreducible representation, that is tau pi, is reduced down to T1G plus T2G plus T1U plus T2U. Now, considering a transition metal complex, only 2 types of ligand group orbitals are available, that are T2G, which is dxy, dyz and dxz, and T1U type of orbitals, which are represented by px, py and pz. The T1U group orbitals are directed toward the ligand and thus are capable of forming strong sigma interactions. Now, if they will be participating in the pi bond formation, then they will conversely weaken the sigma bonding. Hence, their taking part in the pi bonding is not very much favorable. The T2G orbitals, on the contrary, are directed between the ligands and thus can readily form the required pi bonds. The T1G and T2U orbitals remain non-bonding due to the unavailability of the ligand orbitals of the matching symmetry. In the figure 1, we have depicted the identification of the two orbitals of pi symmetry on the each ligand, and we have construction of 12 ligand group orbitals having pi symmetry. Here we will be discussing the type of metal ligand pi interactions which are possible in the complexes. Metal and the ligand orbitals forming a pi bond must lie perpendicular to the internuclear axis. There are various types of pi bonding interactions possible, which are shown in figure 2. They can be named as d-pi, p-pi type of interactions or d-pi, d-pi type of interactions. We can have d-pi, pi antibonding type of interactions and d-pi, sigma bonding type of interactions. In principle, either the ligand or the metal can act as an electron donor. This means a filled d orbital of the metal can donate electrons to an empty ligand orbital or an empty d orbital located on the metal that can revive the electrons from a filled orbital on the metal. The various type of pi overlaps which can be there possible in the metal ligand bonding are depicted in figure 2. The table 2 shows the ligands capable of showing different type of pi interactions. Some of the ligands shown in the table can fall in more than one type of category. For example, iodide ligand represented by I negative has a filled p orbital that can act as electron donor, and it has also low-lying empty d orbitals that can accept the electrons from the metal. The phosphine, a neutral ligand that can accept the electron into its empty d pi orbital or the empty sigma star orbitals. Considering table 2, various type of pi bonding interactions are depicted. Type of pi interactions and how the electrons are donated, and the examples have been listed in this table. For the first type of interaction, that is d-pi p-pi type of interaction, filled p orbitals of ligand are transferred to the empty d orbitals of the metal. Examples include RO negative, RS negative, O2 negative, the halide and R3N negative. For the another interaction, that is d-pi d-pi interaction, filled d orbitals of the metal are transferred to the empty d orbitals of the ligand. In the third type of interaction, that is d-pi pi star interaction, the electrons from the filled d orbital of the metal are transferred to the empty pi star orbital of the ligand. It comprises a very important type of bonding in the ligands such as CO, CN, which are themselves known as pi star acceptor ligands. Another type of bonding possible is d-pi sigma star type of bonding, where the filled d orbitals of the metal transfer their electrons to the empty sigma star orbitals of the ligands. The examples include various type of substituted phosphines and alkanes. The pi orbitals of the ligands can be filled or they can be vacant. Hence, ligands can be electron donors or electron acceptors. The bonding will affect the splitting parameter depending on the mode of electron density transfer. Now we will be discussing Pi acceptor type of ligands. Pi bonding in coordination complexes is feasible with the availability of p or pi star orbitals in the ligands. Thus, here we will consider a class of ligands that are said as pi acceptors, since they can accept electrons in their available orbitals, which is termed as pi-back bonding. This type of bonding has been depicted in figure 3. Hence, for such ligands, the normal bonding along with the back bonding takes place. The bonding is synergic with respect to the back bonding. This means the sigma donation, that is bonding to the metal, reinforces the pi back bonding to the ligand, and the pi donation from the metal to the ligand fortifies the sigma donor component of the bonding. This happens because sigma donation leads to increased electronic density on the metal, which is now amplified by back donation. Conversely, pi back donation reduces the amount of electron density on the metal, which now allows more sigma donation from the ligand to the metal. Hence, it can be said that both are supporting each other. Here in figure 3, the concept of donation and back donation in the Pi acceptor ligands have been shown. A sigma donor and a sigma acceptor type of ligand has been shown. The examples include NH3, CH3 negative and H negative, whereas talking about Pi acceptor type of ligands, the example include CO, NO plus and Cn minus. A filled Pi acceptor ligand has lowest energy as compared to the metal T2G orbitals. The empty pi star orbitals are close enough in energy to the metal d orbitals to allow population. The examples of such type of ligands include CO, Cn, N2, etc. Before proceeding to the molecular orbital energy diagram of such type of complexes, let us first have a look at the molecular orbitals formed by the ligand themselves in order to understand that how the process of donation and the back donation works. Figure 4 represents the molecular orbital energy diagram for the ligand CO. The atomic orbitals of the carbon are represented on the left and the atomic orbitals of the oxygen are represented on the right. In the center we have the molecular orbitals combining the two atomic orbitals. It can be seen that the Homo species, that is highest occupied molecular orbital, is sigma in nature, whereas the LUMO is a pi star 2p orbital, which is empty, representing lowest unoccupied molecular orbital. From the MO diagram CO, it can be observed that it is diamagnetic in nature with a Born order of 3 and has a HOMO of sigma 2p symmetry and LUMO of pi star 2p symmetry. CO ligand is a good Lewis base and a sigma donor at the carbon atom. The vacant pi star orbital or the LUMO can act as an electron pair acceptor, which is capable of forming the metal ligand pi bonds. The bonding pi orbital of the molecular orbital is populated and is largely localized on the oxygen atom because oxygen is more electronegative as compared to that of carbon. Hence, the lower energy, the bonding pi orbital of the MO is populated and is largely localized on the oxygen atom because oxygen is more electronegative as compared to carbon, and hence the lower energy pi bonding orbital is mostly oxygen in character. The pi bonding pi star orbital of the carbonyl has its largest amplitude on carbon and has appropriate symmetry and energy to overlap with the T2G orbitals on the metal. Because of the resulting energy correlation, the pi donor ability of the CO is very small and its bonding to metal is dominated by its pi acceptor character along with the sigma donor ability. This all has been figured out in figure 4. Now we will consider the molecular orbital diagram of the complex which is formed by the complexation of the metal ion with this pi acceptor ligand. Figure 5 represents the molecular orbital energy diagram for the complexes with a pi acceptor ligand. The normal sigma bonding mode gives rise to T2G and EG levels which are separated by a distance of delta naught. When we are talking about the pi acceptor ligand, the energy orbitals of the ligand lie somewhat higher in energy as compared to the metal orbitals. Now, because of the interaction, it can be seen that the actual value of delta naught which was there in the sigma only case has been increased. Pi acceptor ligands are characteristically antibonding with respect to the ligand atoms and hence they are elevated in energy as compared to the d orbitals of the metal. The molecular orbitals are formed which are T2G in symmetry and principally of metal d orbitals in nature. They are at lower energy than the metal d orbitals. This results in greater value of delta naught as compared to that of before because the decrease in energy the bonding T2G symmetry molecular orbitals. Now we will be taking the case of the pi donor ligand and how their molecular orbital diagram is related to them. A pi donor ligand has filled orbitals that have pi symmetry around the metal ligand axis. The energies of these orbitals are same as that of metal d orbitals and there are no vacant low energy pi orbitals for such type of ligands. The examples of these include Cl negative, OH negative and H2O which are represented as the pi donor ligands and also which are very weak field ligands. This decreases down the value of delta naught. The mode of donation for the pi donor ligands have been represented in figure 6. Here we have discussed the concept of donation of pi donor ligands, that how the electron is donated in these ligands. All ligands are sigma donors. Ligands with filled p or d orbitals may also serve as pi donor ligands. Example of pi donor ligands are I negative, Cl negative and S2 negative. The filled p or d orbitals on these ions interact with the T2G set of orbitals represented by dxy, dyz and dxz on them. The metal to form a bonding and antibonding molecular orbitals. The bonding orbitals which are lower in energy are primarily filled with the electrons from the ligands and the antibonding molecular orbitals are primarily occupied by the electrons from the metal. The size of delta naught decreases since it is now between an antibonding T2G orbital and the Eg star orbital. This is confirmed by the spectrochemical series. The weak field ligands are also pi donor ligands. In figure 7, we can see a molecular orbital energy diagram for the complex which is having pi donor ligand. The original delta naught value which was between the T2G orbitals and the Eg orbitals has been diastrically the value of delta naught which was initially between the T2G orbitals and Eg orbitals of the sigma donor ligands only is specified by delta naught which has greatly been reduced down since now the T2G orbitals of the filled pi orbital are somewhat lower in energy as compared to the metal orbitals. This leads to the destruction in the value of delta naught and lowering it down. The filled Pi star or p orbitals on the ligands can give rise to ligand to metal pi donation, which then results in smaller value of delta naught for the complex, whereas when we have an empty higher in energy p or d orbital on the ligand, it results in the metal to ligand pi donation, which then leads to increase in the value of delta naught for the complex. Ligand to metal pi bonding usually decreases the stability of the complex, which then favors high spin configuration, and in case of metal to ligand back donation, the pi back bonding leads to increase in the stability of the complex, which then favors low spin arrangement. All this has been depicted in molecular orbital energy diagram for the complexes with pi donor versus pi acceptor ligands. Both of them have been compared. On the left hand side we have pi acceptor ligands and on the right we have pi donor ligands. Now it can be seen that how the delta naught value is altered in both the cases. When we talk about pi acceptor ligands, the delta naught value is drastically enhanced, whereas when we talk about pi donor ligands, the value is drastically reduced. Hence we can say when we talk about pi acceptor ligands, they form basically the low spin complexes, since the complexes are formed from the ligands which do not have the tendency to cross the delta naught barrier. Now we'll go to the summary which highlights the points resulting in this module. The ligand group orbitals that can form the pi bonds in the octahedral complex come under the four type of symmetry categories respectively named T2G, T2U, T1U and T1G. The T1U group orbitals are directed towards the ligand and thus are capable of forming strong sigma interactions. The T2G orbitals on the contrary are directed between the ligands and thus can readily form the required pi bonds. The T1U and T2G orbitals remain non-bonding due to the unavailability of the ligand orbitals of matching symmetry. Metal and ligand orbitals participating in the pi bond formation should lie perpendicular to the internuclear axis. The types of pi interactions possible in this case are d-pi, p-pi type of interactions, or we can have a d-pi, t-pi type of interaction. Next we can have d-pi, pi star type of interaction or d-pi sigma type of interaction. A pi acceptor ligand is a ligand that has filled orbitals much lower in energy as compared to the metal T2G orbitals. The empty pi star orbitals have same energy, therefore metal d orbitals participates in filling up of the orbitals. The examples of such type of ligands include CO, Cn, N2, etc. Now the ligands which have filled p or d orbitals may also serve as the pi donor ligands. The examples of this type include I negative, S2 negative, which act as very good pi donor ligands. Ligand to metal pi bonding usually decreases the stability of the complex, which then favors high spin configuration, and in the case of metal to ligand back donation, the pi bonding leads to the increase in the stability of the complex, which then favors low spin configuration. Thank you.